Promised you some polynomial theorems, and here they are. They look pretty impressive with all these roots and fancy language, but actually, you already know most of these. The very first one, which they call the fundamental theorem of algebra, and most of you folks have spent 2 years studying algebra. This is its fundamental theorem. And you already know this. If the polynomial has degree n, then it has n roots. That the degree on the polynomial tells you how many roots. That includes, as I say here, triple roots and double roots. It also includes imaginary roots. Not just where it crosses the x-axis, but imaginary roots are included as well. So if we know the degree, you know how many roots to expect. The next two theorems actually come together, and some textbooks include them all as one. They are doing the conjugates of square roots. So if a plus the square root of b is a 0 or a root of the polynomial, automatically a minus the square root of b has to be a root. They come in pairs. So roots with radicals come in pairs. I should say roots with square roots. Come in pairs. And that's why we had to subtract 2 when we were doing the rule of signs stuff. Well, this is obviously square root, but this just says a plus bi. Well, you know, of course, that I is the square root of -1. So this is actually a square root problem. So if a plus b times the square root of -1 is a root, then a minus b times the square root of -1 has to be a root. It's just saying that if it's got a square root in it, it can't be simplified, then they're going to be pairs. You're going to have these conjugate pairs. Which means if you know one root, automatically you know the other root. It's going to make it faster to solve things. So they tell us that here, that if 1 plus I times the square root of 2 is an answer, so is 1 minus I times the square root of 2. This is all one number here. 3/2 plus the square root of 5 is one number. So is its conjugate, 3/2 minus the square root of 5. And if one of these is a solution to the polynomial, they both have to be solutions. And they tell you they're both solutions of this particular polynomial right here. This one, odd degree polynomials. They're saying it's got to have at least one real root. Well, the roots are like the x-intercepts. Which means where the graph crosses the x-axis. So odd degree, like a cubic function. Picture the shape of its graph. Sort of like this. Its end behavior, it's going in opposite directions to infinity. It has to cross the x-axis. It does not have a choice. If it was a negative quintic, so it would have sort of a negative slope. And it could have two little loopy things. so that it would have 4 different turning points. Once again, because of its end behavior, it has to cross the x-axis. Even degree functions don't have to if they don't want to. You can have a parabola that doesn't cross the x-axis, has no x-intercepts. Okay, this fifth one is kind of weird. They said it's an interesting relationship. This is your basic polynomial. A times x to the highest power that we've got, plus b times x to the next highest power, plus c times x to the next highest power. The powers are going down all the way till the end where you get the constant and there are no x's at all. Saying that the sum of the roots is going to be the opposite of b divided by a. So if this was a 5th degree polynomial, if you added up all 5 roots, they would have to equal the opposite of b divided by a. Do you remember that to get the axis of symmetry for a parabola, that was negative b over 2a? Well, this is negative b over 1a. And I wanted to bring that up because it has been on some of the SAT exams. They'll ask you a question, they'll give you a polynomial, and they'll ask what is the sum of its roots. So people factor it out, find out what all the different roots are, and then they add them up. When you only get 1.5 minutes per question, it's a lot faster if you know this little gimmick. This only works for polynomials. The product of the roots, like if you multiplied all 5 roots together, is going to be whatever the constant is, whatever this constant is, on the end, divided by the leading coefficient. If the polynomial is even, now if the polynomial has an odd degree, for instance, if it was a 5th degree polynomial here, then it's going to have to be the opposite of whatever k is over the leading coefficient. And that will tell you what the product of all the roots is. So they give us some examples down here. Say if we have this polynomial, 3rd degree polynomial, then the sum of its roots would have to be the opposite of negative 5 divided by 2. That's what they got. Now the product, because this is in odd degree cubic, the product is going to be the opposite of k, the opposite of that final constant divided by the leading coefficient. So they're going to do negative 9/2. They gave us this equation. They said the sum of the roots is 0. Well, sum of the roots is supposed to be negative b over a. But there is no, we start off with x to the 4th. This is really, although they didn't write it, this is really 0 x to the 3rd in here. So b is really 0. So negative 0 over 1. That would mean that all 4 roots, if you added them up, would cancel each other out, and the total would be 0. The product of the roots, now this is an even degree, so it would just be whatever the constant is divided by whatever the leading coefficient is. And that's where they got the 3. So they look pretty impressive, but they're not that bad. More little gimmicks and some stuff that you've known for a long time.